We want to use a triple integral to determine the volume of the tetrahedron with the following four vertices. Let's first take a look at this in space. If we were to plot these 4 points, it would form this tetrahedron bounded by the blue plane and the 3 yellow planes, which are the 3 coordinate planes. So our goal here is to find the volume of this tetrahedron. Now, if we didn't have graphing software, we'd still want to graph this. So using the x, y, and z axes, we would plot these 4 points. So we have this point here at the origin. The x-intercept is 3, 0, 0 here. The y-intercept is 0, 4, 0 here. And the z-intercept is 0, 0, 5, which would be here. So this would be the tetrahedron, again, that we're trying to find the volume of. Notice how it's bounded by the first octant, or the 3 coordinate planes, and this plane here, where we know the 3 intercepts. The volume of a solid region D is given by this triple integral, where we integrate over the region D, which again is the closed solid region. Notice how the integrand function is just 1, and differential v can be any of these 6 possible orders of integration. So let's go and set this up as the volume v equals the triple integral. And let's go ahead and include 1 as the integrand function. And let's use the order of integration of integrating with respect to z first, then y, and then x. Any order would work, but let's go ahead and use this order of integration. So now we'll determine the limits of integration for z. We'll notice how the solid is bounded by the xy plane, which would be z equals 0, and it's bounded above by this blue plane. So now we need to find the equation of this blue plane, which we can do because we know the intercepts. But again, we know the lower limit of integration with respect to z is going to be 0. And the equation of the plane with these 3 intercepts is given by this equation. So because the x-intercept is 3, we're going to have x divided by 3 plus the y-intercept is 4, so we have y divided by 4, plus the z-intercept is 5, so we have z divided by 5 equals 1. And now if we solve this equation for z, we can determine the upper limit of integration for z. Now if we integrate with respect to a different variable first, we'd have to solve this equation for whichever variable we integrate with respect to first. But we'll solve this for z, so we'd have z divided by 5 equals 1 minus x divided by 3 minus y divided by 4. And now I'll multiply through by 5. So we have z equals 5 minus 5/3 x minus 5/4 y. Again, this is going to be the upper limit of integration with respect to z. And notice how we have z expressed in terms of x and y. So we have 5 minus 5/3 x minus 5/4 y. And now we need to find the limits of integration for y and x. To do this, we'll want to have the xy trace. In general, to determine the xy trace, we set z equal to 0. So notice if z is equal to 0 for these 4 points, we'd only have 3 points to consider, 0, 0, 3, 0, and 0, 4. And I've already plotted these 3 points in the xy plane, so we can determine the limits of integration for y and x using this triangular region here. I also included the yz and xz traces. We don't need those for this example because of the order of integration that we're using, but if we change order of integration, depending on the order, we'd have to use one of these traces instead. We're going to need the equation of the line that contains this side of the triangle. There's 2 ways of doing this. We could set z equal to 0 and solve this equation for y, which would take some work. It's much easier to recognize that the vertical intercept is 4, and the slope would be down 4, right 3, so the slope is negative 4/3. So the equation of the line containing this side of the triangular region would be y equals 4, the vertical intercept, minus 4/3 x. So with respect to y, we integrate from y equals 0 to y equals 4 minus 4/3 x. So again, we have from 0 to 4 minus 4/3 x. Notice how we express y in terms of x. And again, these are the limits of integration for y because this area in the xy plane is bounded below by y equals 0, and bounded above by y equals 4 minus 4/3 x. And finally, the limits of integration for x would be from x equals 0 to x equals 3. So this triple integral will give us the volume of the tetrahedron. Let's evaluate this on the next slide. So we first integrate 1 with respect to z, which would just be z. So we have the double integral, and again the antiderivative is z. Notice when we evaluate big F of b minus big F of a, we're just going to have this quantity minus 0, which means for the double integral, the integrand function is just going to be the quantity 5 minus 5/3 x minus 5/4 y. Now we integrate with respect to y, treating x as a constant. So we'd have 5y minus 5/3 xy, and then we'll have minus 5/4 times y squared divided by 2, or 5/4 times 1/2 y squared. That'd be 5/8 y squared. Now this starts to get messy. We need to find big F of b minus big F of a. So we'd have the integral from 0 to 3 of, we substitute 4 minus 4/3 x for y, so we'd have 5 times the quantity 4 minus 4/3 x minus 5/3 x times 4 minus 4/3 x, and then minus 5/8 times the quantity 4 minus 4/3 x squared. So there's big F of b, and then for big F of a, of course, each of these has a factor of y, so we'll just get 0. Now let's go ahead and simplify all of this. Let's go ahead and distribute here and here, and then we'll go ahead and square the quantity 4 minus 4/3 x. And now we'll distribute here and then combine like terms. And now let's combine like terms. So we have 20 minus 10, which is 10. Let's look at the x terms. These two x terms are opposites. So we just have minus 20/3 x. Looking at the x squared terms, we have 20/9 x squared minus 10/9 x squared, which would be positive 10/9 or plus 10/9 x squared. And then finally, we integrate with respect to x. So we'll have 10x and then minus 20/3 times x squared divided by 2. That's going to be minus 26 x squared. And then plus 10/9 times x to the third divided by 3, which is going to be 10/27 x cubed. So when x is 3, we have 10 times 3 minus, I know 26 simplifies to 10/3, but I'm going to leave it as 26 times 3 squared plus 10/27 times 3 cubed. So all of this minus, when x is 0, notice all the terms would be 0 because each has a factor of x. And this simplifies perfectly to 10, which means the volume of the tetrahedron would be 10 cubic units. Which again would be the volume of the tetrahedron shown here, bounded by the blue plane and the 3 coordinate planes. I hope you found this helpful.